which is the magnetic field of a bar magnet. So this lab was intended to show us how to analyze the behavior of a bar magnet, how to compute the magnetic moment of the bar magnet using the strength of the magnetic field at various locations, like 45 degrees to it, parallel and orthogonal to it, as well as to explain possible plausible reasons for differences between our experimental data and a computational model of the bar magnet. A preview of results, we found N to be minus 2.1734, and that's amp meters squared. K was found to be 1.64. The experimental magnitude of the magnetic field at 45 degrees to it at a certain distance was 12 times 10 to the minus 5 Tesla. And the computational model of the same location at the same distance showed an expected value of 2.6 times 10 to the minus 5 Tesla. So this is an order of magnitude difference between the experimental and computational data, and we'll explore possible reasons for this later. Some fundamental principles: we use the equation for the magnetic field of a dipole, like a bar magnet is a dipole. So this was used later, we'll discuss that. The magnitude of magnetic field from a bar magnet is K times R to the N. And we also used a Python environment to predict the magnetic field of the bar magnet at various observation locations using these fundamental principles. So here was the setup as shown. We used a smartphone as magnetometer. So the system involves the magnet, the phone, and the Earth. The surroundings are everything else, which is full of EMF, and we'll discuss that again. The location of the magnetometer and the phone was determined. This image actually shows pretty accurately where we determined it to be, and then we measured the strength of the field from a known distance via this yardstick. Here are the results. These are the results of the magnetic field strength at various distances, and these are the results of the field strength at 45 degrees. This plot shows the natural log of Bx versus the natural log of R, and we get this equation. To analyze this equation, you'll see it's in y equals mx plus b format. So this term n is minus 2.1734, which is n. And then we can solve for k. The b term here is the natural log of k, so we determine k to be 1.64. So here's a preview of the computational model. This is the bar magnet. These orange arrows are the parallel n-axis magnetic field strength vectors. The blue arrows are the orthogonal magnetic field vectors, and this cyan purple arrow is the 45 degree observation location field vector. Here are the results showing our computational magnitude of B at 45 degrees, 2.6 times 10 to the minus 5 Tesla. Here's the code. This function here computes the dipole using this equation that I showed earlier. This code creates the arrows and solves for their intensities. So there are some big assumptions we make in this experiment. Firstly, we assume the bar magnet is perfect with a perfect magnetic field, and arguably most importantly, we assume the bar magnet and the Earth are the only other magnetic systems affecting, or only other magnetic sources in the system. This experiment was performed inside in the physics lab, so there is a lot of other EMF that would be manipulating our results. As well as the phone magnetometer, we found to be very unreliable. We would get very inconsistent results from placing it at the same location, and it was also a bit uncertain exactly where the magnetometer was within the phone. Now some discussion questions. What if we hadn't oriented our experiment to compensate for magnetic north and had laid out the meter stick at some intermediate angle with respect to the magnetic field? Well, if we had done this, then Earth's magnetic field pointing north would have had some y component that would have added to the observed magnetic field, which would increase our observed strength of B and thus manipulate our results. And lastly, if we were to stick two identical magnets end to end and run the experiment again, how would our measurements differ? The strength of the field would double because you're doubling the size of the magnetic moment, and as such, the strength of the B would double. Okay, so to answer these questions as well, when the magnetometer is far away from the magnet, it measures a near zero magnetic field. This is true. As the magnetometer moves closer to the magnet, the measured X component decreases. That's false. It should be increasing. Position of the magnetometer has no effect on the measured X component. No, I mean, as you move the phone and thus the distance of the magnetometer to the magnet, the strength of the magnetic field will change because you're moving its position of the magnetometer. As the magnetometer moves closer to the magnet, the measured X component increases. Yes, this is true, as I previously said.